Computer chips. Most of these designs target matrix vector multiplication, MVM, matrix multiply accumulate, MAC, because that dominates. Transformers, attention plus MLP, vision models, robotics, perception stacks, optical, photonic approaches can compute those operations by letting physics do the math, the common trick. Weights stored in physics. Instead of fetching weights from SRAM, HBM and multiplying digitally, the chip stores weights as physical parameters, phase shifts, interference patterns, metasurface responses, or programmable optical elements, sends light through, onto that structure, and the output light intensity encodes the multiply result. This is closely aligned with what your summary says, weights physically stored in the metasurface. Light performs multiplication instantly, and it matches the broader literature on metasurface, diffractive optical computing and optical neural nets. 2. The metasurface plus optical transistor claim, and what we can actually substantiate. Recent reporting describes Neurophos as pursuing metasurface-based optical computing with extremely small optical switching, modulation elements, framed as optical transistors, claiming very large matrix engines and big efficiency upside, but also noting its early and volume production is not imminent. Key corroborated points from the coverage. Texas, Austin-based photonic AI chip startup, Neurophos, metasurfaces used for high-speed silicon photonics, in-memory style processing. Claims of optical transistors, far smaller than prior approaches, promising dense, fast optical compute blocks. Timeline risk. Testing, ecosystem building, scaling, manufacturing hurdles. Not, swap GPUs tomorrow. So, the direction is real. The specific performance claims should be treated as provisional until there are peer-reviewed device papers, customer benchmarks, and manufacturable yield data. 3. Why optics can be drastically more energy efficient than GPUs. In principle, GPUs burn power in two main places: data movement, especially memory left-right arrow compute, switching transistors billions of times per second. Optical compute attacks both. Light propagation has no electrical resistance, so you avoid certain resistive losses, though lasers, modulators, detectors still cost power. Optical interference can implement linear algebra, in one shot, massively parallel. This is why photonics is repeatedly framed as a response to the AI energy wall. 4. The hard engineering truth, precision, noise, and hybrid reality. Analog optical compute is not free magic. The big constraints are well known. A. Numerical precision. Optical analog cores tend to excel at low precision inference, int4, FP4-ish equivalence, sometimes 8-bit-ish in practice depending on architecture. High precision training is harder because analog noise accumulates and calibration is constant work. B. Noise, drift, thermal stability. Your summary mentions thermal stability. This is absolutely a real issue. Photonic devices are temperature-sensitive. Metasurface responses can drift. Maintaining calibration over time is non-trivial. C. You still need electronics. Even optical compute systems usually need ADC, DAC, detectors, digital control loops, memory hierarchy, scheduling, software stack. So, the winning architectures are typically hybrid. Optics for the heavy linear algebra, electronics for control, nonlinearity, and everything else. The research literature and industry commentary consistently land on this hybrid conclusion. 5. How these ties into the other giant trend, optical interconnect, data movement. Even if optical compute cores take longer, optical links are already becoming central because data movement is the bottleneck. Reuters reported major momentum in co-packaged optics and photonic fabrics for chip-to-chip connectivity, but also that reliability, ecosystem, and deployment timelines still matter, with some expectations that broad adoption could take years. This matters because many photonic compute companies first win by reducing power and interconnect, increasing bandwidth between GPU memory pools, then expanding into compute. 6. Why this is exciting for humanoid robots. Your angle is spot on. Humanoids have brutal constraints. Swap, size, weight, and power, heat dissipation, real-time latency, battery life. Photonic, analog compute could help in 3 ways. 1. Always-on perception at lower power. Vision stacks, multi-camera, depth, SLAM features, are matrix-heavy. If an optical accelerator can do key layers at lower joules, you can keep perception running longer, reduce cooling hardware, shrink compute volume. 2. Smaller, edge AI bricks. If the claimed density gains materialize, big, matrix engines, in small area, you can pack more inference into a humanoid torso without building a mini data center inside the robot. 3. Battery budget reallocation. Every watt you save on compute can go to actuators, balance, control, sensing, comms. The realistic near-term best fit is optics for specific hot kernels, CNN, transformer blocks, plus standard electronics for everything else. 7. What to watch for before betting the robot roadmap on it. Here's a clean due diligence checklist. This is the wizard engineer filter, real benchmarks, not just peak tops, latency, sustained throughput, model accuracy, impact, batch size, assumptions, precision plus stability. How often must it calibrate? How does temperature affect accuracy? Programmability. Can you reprogram weights quickly? Is it static per model? Does it support sparsity? I/O bottlenecks. If the optical core is fast but you choke on ADC, DAC, memory, gains evaporate. Software stack, compilers, PyTorch integration, kernel coverage, debugging tools. This is where GPU ecosystems are brutally strong. Manufacturing pathway. Can it be made in standard silicon? Photonics flows at useful yields. 8. Practical recommendation for global robotics today if you want to position your humanoid program to benefit without waiting years. Architect your robot compute as modular accelerator slots, PCIe, CXL-like abstraction at the system level, even if embedded. Keep your models quantization ready. Int8, Int4 pipelines, distillation, calibration tooling. Design thermal plus power budgets to allow a future photonic module swap in. Track 2 categories separately. Optical interconnect, sooner. Optical compute cores, later. But potentially huge. Robert Coley, Global Robotics Corporation.